Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments. For tonight, we're going to continue a three-part series on taking a look at how you can best prepare your students for the upcoming AP Calculus exam. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight I'm excited to be joined by our two panelists, Vickie Carter and Steve Kokoska. Vickie's been teaching high school math for 44 years at West Florence High School. She's a former co-chair of the AP Calculus Development Committee and served as an exam leader at the AP Calculus reading in the summer of 2018 and 19. She received the T-Cube Leadership Award in 2015, and Vickie has served on TI-Nspire authoring teams and has presented at many national, state, and local conferences. Vickie, we're excited to have you with us tonight.
Welcome, everyone. We're glad you're joining us for this webinar tonight.
And Steve is a professor in the Department of Mathematical and Digital Sciences Department at Bloomsburg University. He is a former chief reader for the AP Calculus reading and a member of the Development Committee. Steve's an active T-Cube instructor and a College Board consultant with recent workshops in China and Singapore. He just published an AP Calculus text and the third edition of his introductory statistics text. Steve, it's great to have you with us tonight.
Thank you very much, Michael. I'm delighted to be here. You know, it's always enjoyable to talk about the scoring of the AP Calculus exam and just to talk with you and Vickie about AP Calculus in general. So thanks.
Thanks, Steve. We're expecting a large crowd, so your audio is muted. Feel free to say any questions you have for Steve or Vickie using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues tonight, but in the event that you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. At this point, Steve is going to discuss our agenda.
Thanks very much, Mike. We've already taken care of the welcome and introductions. I'm going to start off tonight by talking about AB4 BC4 from the 2019 AP Calculus exam. So I'll very quickly review the question and the scoring guidelines. And I'm going to spend a lot of time talking about or giving a brief briefing, talking about how those scoring guidelines were interpreted. And when I finish with that, I'm going to pass the screen over to Vickie, and she's going to talk a little bit about technology strategies and how you'd use TI technology to maybe illustrate the solution to this problem, maybe explore the solution of this problem. And then towards the end, she's going to pass it back to me, and I'm going to talk about a few problem extensions. As you know, these free response questions are very rich. They start out in development with probably about 30 or 40 points, and they get whittled down to 9. And so I'm going to give you a couple of extra questions that you can work on with your students, some AP Calculus type questions. And then at the very end, I guess, Michael, I understand we have a webinar drawing. Is that for a black Lexus tonight?
Similar. It's actually going to be for the T-Cubed International Conference. You may see a black Lexus drive around in Dallas when we're at the conference, but yeah, it'll be for the T-Cubed International Conference coming up this March. So thanks, Steve. And Vickie is going to discuss our expected outcomes.
So Steve is going to do a very nice job of discussing the 2019 AB4 BC4, which is a differential equation question. He's going to talk about the scoring guidelines. We hope that you will understand how the scoring went a little better after our discussion tonight. We will, as Steve said, look at some technology. Steve's going to repeat this, but I'm going to go ahead and say it now. This was not a technology active question, but we feel that student understanding of how technology may help them while they're actually learning this concept is very important. So we're going to demonstrate some of that for this particular question and maybe some similar to it. And then Steve has those nice problem extensions that he will talk about after we do our little technology piece.
Vickie, thanks so much. Steve, you should have control. Feel free to share your screen.
All right, here we go.
So Steve's getting that up. Just a couple things to share with you. First, as I mentioned, this is the second in a three-part series. In case you missed part one, you don't need necessarily part one to participate with us tonight. And towards the end of the webinar, I'll show you where you can go back and get part one and also register for the upcoming part three. Second thing is Steve's going to be doing a really nice job of displaying the question, the actual AP question, as he's talking about the scoring guideline at the same time. So if that's too small on your screen, you can kind of manipulate your windows to make that screen larger. Also, one way to do that is the very top of your WebEx screen. There's a little icon, and you can hover over that icon, and it'll let you go full size with what Steve's presenting. Thanks so much, Steve.
Okay, thank you very much, Michael. So on the left-hand side of my screen, I'm going to leave this up here because it's kind of nice to be able to refer back to the statement of the problem. So that'll be there throughout my presentation. And on the right-hand side of the screen are a bunch of slides here that talk about the scoring of this problem. So let's start out by just taking a look at the statement of the problem. So this question involved a cylindrical barrel. And I should probably stop right there. Students made this problem a little bit more complicated than it actually was. This was a cylindrical barrel with constant diameter of 2 feet and therefore a constant radius of 1 foot. And it had some collected rainwater in it. And we're also told that this rainwater drains out of the bottom of the barrel. Now, the rate of change of the height h of the water in the barrel with respect to time t is given by this expression down here. And I'm just going to step back for a moment. Vickie was kind enough to remind me about this. In this differential equation, you'll notice that there is no independent variable t present. It's not on the right-hand side. It's not on the left-hand side. And for whatever reason, that often gives students trouble, especially in a problem with context like this one. Not sure why. It's actually easier, we think. But there was no t on the right-hand side here. And we're reminded, I think at the bottom of this problem, we're reminded that the volume of the cylinder, with radius r and height h. So in part A, we need to find the rate of change of the volume of the water in the barrel with respect to time when the height of the water is 4 feet. Okay, sounds pretty reasonable. In part B, we need to determine whether the rate of change of the height of the water with respect to time is increasing or decreasing when the height of the water is 3 feet. Now that's a little tricky because we're asking students to tell us something about the rate function. So that's a little different, but nevertheless the solution technique here is the same. The concept is the same. And in part C, we're given an initial condition, and son of a gun, we need to solve a differential equation for h in terms of t. Now, I just want to remind you here that this was, again, a non-calculator active question, but we're still going to show you a little bit about the calculator. And I think Vickie wanted to remind you something about learning outcomes. Is that right, Vickie?
I did. So I want to remind everyone that these are very rich problems that can provide you with some other resources. For instance, the first learning objective in this unit in the new framework says that students would be able to interpret verbal statements of problems as differential equations involving a derivative expression. So before my students ever solve a differential equation, I might give them a verbal statement such as the rate of change of the height of the water in the barrel with respect to time is directly proportional to the square root of the height, and ask them to interpret that statement as a differential equation, hoping that they would write dH dt equals k times the square root of h. And we practice some of these with direct proportion statements and inverse proportion statements and some other various types of scenarios so that they are accustomed to writing a differential equation before they actually have to solve them. And it seems to be a very valuable experience for the students to do that.
Great idea, Vickie. So here's a look at the scoring guidelines. So part A was worth 2 points. The first point was for finding dV dt, so the rate of change of the volume with respect to time. And so a way that I kind of think of the first point here is that it's in some sense this is a conceptual point. It's for the student understanding, first of all, that this is a related rates question, and for taking the derivative of both sides of this expression, v equals pi r squared h, with respect to t. And the second point here was for using that expression for dH dt, produce a correct answer, and be careful in this part A, they also needed to produce the correct units. So down here in part B, this was worth 3 points. This divided up kind of nicely. The first point was essentially a power point rule. A power rule point, how about that? For finding the derivative of minus 1/10 times the square root of h. So it was 1 point for actually coming up with this expression right here. And then the second point was related to the chain rule. It was a chain rule point. So for finding d squared h over dt squared, we need to multiply by the derivative of h with respect to t. So it's for including this expression right here at the end of this second derivative. And then finally, the third point was for the correct answer with an appropriate or a suitable explanation. Cool. Part C was worth 4 points, and the division of these 4 points has become pretty constant now, pretty routine in a differential equation problem. So the first point was for separating the variables, for getting all the h's on one side and all the t's on the other. Now, note, if there's no evidence of any separation of variables at all from the student, and some of this is professional judgment, the student would earn 0 out of the 4 points here. The second point was earned for 2 correct antiderivatives. So right in here, I can see the derivative of the left-hand side, the derivative of the right-hand side. I'm not looking at that C yet. The third point is a little different from, say, 5 years ago, but it is now pretty constant. It is for including, or routine, it is for including the constant of integration in a correct manner, in the correct place, and for using the initial condition. So for including this plus C, and for using the initial condition, there's the t equals 0, and there's the h equal 5. Now, if a student does not include a constant in integration, the most that they can earn in this part of the problem is just the first 2 points. That's this note over here at the bottom right. And finally, the fourth point was for producing the correct explicit expression for h of t. So that means that the student must actually solve for h in terms of t here. So they can't just leave their solution like this in this line. Okay, so I'm going to talk a little bit about student performance in very general terms, sort of at a high level. So I'm able to take a look at the question leader reports, and this is what I've garnered from reading some of those. So some general comments about student performance. In Part A, this is good. Many students recognize that this was indeed a related rates problem, or a related rates question. However, some students simply couldn't find the derivative of the expression for volume with respect to time. Just couldn't do it. And some common errors here. Well, unfortunately, some students took the radius to be 2. They read diameter as radius, and they took the radius equal to 2 instead of 1. Now, don't panic. We're able to give some students some appropriate points for good calculus work here. Another common error here was the incorrect derivative of v with respect to t. I don't know if you can see this on the screen, but here are 2 common errors. And I thought, Mike, if it's okay, I might ask a question or 2 here of participants. This is a common error. This is a common error in finding dv dt. Can you tell what some students, not your students, but some students did wrong in this expression? I can't see the chat window, Mike, but if anybody responds to that.
Sure, I'll let you know.
Can you see what a student may have done wrong here? I mean, I kind of see that dH dt in there, and that's a good thing. But what happened over here in this expression?
So we have Oscar said they derived r, but it should be a constant.
Very good. Yeah, what we think happened is students took the derivative of r. So they got 2r here, and the 2 ended up out in front. Yeah, this was a common error. Very good. So here's another common error in this expression on the far right-hand side. I'm sorry if that highlighted badly. I kind of like what's over here on the right-hand side, and okay, I'll give you a little bit of a hint. It certainly looks like a student who wrote this is using the product rule, but there's an error here also. Can you see what the error is here? Yeah, I think I see that. Someone said they forgot the dr dt. That's exactly correct. Over here on the left-hand side, they didn't put in the dr dt. Okay, for 25 bonus points, then if they had the dr dt in there, what would dr dt be equal to? Yeah, exactly. It would be 0. And so this turns out, and I'm going to mention this again a little later, it turns out that this is a valid way to approach the problem. If you have the dr dt in there, but you have to recognize that the change in the radius with respect to time is 0. Very good.
So
Excellent.
Steve, it
Yes.
makes you wonder if the students actually recognized that the radius was a constant but didn't know how to handle it. So possibly their way of handling it was to kind of ignore the part where they're taking a derivative of r with respect to t. I don't know if that's what it is, but it does seem to be sort of in that direction.
Yep, and we saw this enough that it showed up on the question leader reports. So yeah, very interesting. And unfortunately, some students in this item right here, some students actually made this problem harder than it was. They thought that this involved some proportions. And I'm sure that you teach this problem involving an inverted cone where you have similar triangles. And I think many students remembered that problem and used this relationship between r and h. And unfortunately, that's incorrect here. So in part B, unfortunately, many students simply evaluated dHdt with h equal to 3. That's certainly not right. And some students only differentiated this expression with respect to h. They did not employ the chain rule. Take a quick look at part C. So this is a good thing. In part C, many students did correctly separate the variables, and they were able to integrate both sides. They were pretty easy, straightforward integrations. Most students were able to do that. Most students correctly included a constant of integration. I probably should have added this on the slide at the appropriate point. But there were some common errors here, and I hope these are showing up in red. This first one here I kind of think of as a universal logarithmic anti-differentiation rule, which certainly isn't correct. But unfortunately, many students still use this rule. And this is another common error here that we saw from students as they tried to solve explicitly for h. At least at my university, we call this a freshman's dream in squaring a binomial. You don't have to worry about those middle terms, I guess. So let's take a little bit closer look at these parts. Let's look more carefully at the scoring guidelines. So again, the first point in part A was for finding the derivative of v with respect to t. And to earn this point, we really need to see evidence of the chain rule, that is the derivative of h with respect to t. So here are 5, I think, bulleted items, and I think every one of these responses earns the point if I can explain them to you. So in number 1 here, each one of these, or in the first bulleted item, each one of these responses would earn the first point. I think you can probably agree we can see in each one of those responses, we can see the pi times, we can see the dHdt, and we can see that the radius is equal to 1, implied at least in those 3 versions. In these 3 responses, or in these 2 responses, pardon me, the student is using the product rule. Now, they haven't yet used the fact that the change of r with respect to t is 0, but you know what? That's okay. This still earns the first point. I frequently get a question about notation, and we understand r prime and h prime in the context of this problem. We'll accept that. That's okay. Over here, the student has substituted r equal 1, and that's okay. Here, they've got pi r squared. They haven't substituted in 1 yet. That's okay. Here they've substituted in r equal 2, but you know what? We decided that they still conveyed the concept of the chain rule, and so they would earn the first point, but they're not going to get the second. In this first response over here, the student has used the explicit expression for DHDT. That's okay. And this response right here, I often talk about this sort of line in the sand, and boy, that's right on the line. That's pretty darn minimal. And I'm not sure I'd even give credit for that in my class, but it still conveys the concept, and we decided that it earns the first point. Now, down here at the bottom in this last bulleted item, I think this is kind of interesting. Over here, if the student wrote those two expressions, they would earn the first point. And the reason is because we know where the 4 came from. We believe what has happened here is that the student has substituted in, let's see, they've substituted in r equal 2. They're telling us that's the expression for volume. I can see that they've taken the derivative of h with respect to t. They've used the chain rule. They're good for the first point. However, if this is the only expression that they write down, I don't know where the 4 came from. It might have come from, as we were talking about a couple moments ago, sort of that derivative of r, 2 times r. So there isn't enough there for them to earn that first point. That's subtle, but that's the way we decided to grade it last summer.
But Steve, this is this is a perfect example of it being the student's responsibility to show us how their work is developing as they get to their answer. And they've got to show some steps. And some students seem to think that they are trivial steps, that why should I be writing this down? But it's just so important on the AP exam, especially if they make a mistake, that we have something to go by, that we know where the mistake is coming from and perhaps can give them some credit for the problem.
Yeah, and I think, Vickie, you and I have talked about this a lot, about how important communication and notation is important, how important those two things are. Students have to tell us what to do, and we have to be able to follow a logical argument. So absolutely, yes. I agree with you. I agree. So still looking at Part A, here are a couple of expressions that do not earn the first point. This is sort of a duplicate of what we saw and read a couple of slides ago. We don't see it. Or here the student has taken the derivative of r, but we don't see a dr dt in there. And let's see, in this one, what's happened here? We believe that the student has taken the derivative of r, and they had the dh dt in there, but you're not going to give them the point there. They've taken the derivative of r. Okay. Now, the second point in Part A was for the answer with units. Remember, we don't always ask for units, but we did here. So we're looking for something like this, minus pi over 5 times minus pi over 5 cubic feet per second. Again, this was not a calculator active question, but we allowed students to use an approximation for pi of 3.14. That would be okay if they gave us that response. Bald answers here in general earned no points in Part A. What's a bald answer? That is an answer, only an answer, where some supporting work is expected. Now, it was possible for a student to give us some sort of reasonable work and an answer with units and earn a 0-1, but in general, bald answers got 0-0. So sorry, I seem to be belaboring this point, but I'm still looking at Part A. Here's a couple more specific examples in how each one was scored. So in this first example, this response here, these two lines or two responses here, would earn a 1 and a 0. I can see the derivative right here, pi dh dt. That's the first point. But this answer right here is ambiguous. We have to read that as pi minus 1/5. Communication, notation is important. That student does not earn the second point. In example 2 here, the derivative is wrong. Now, it's still possible to earn the answer point with some reasonable work, but, well, there isn't any here. And besides that, the answer is wrong. So this earns a 0-0. Let's see. In 3, the student uses r equal 1. Over here, finds dv dt. Uses the expression given in the statement of the problem for DHTT and leaves the final answer unsimplified. And that's okay. This is a final numerical answer. Doesn't need to be simplified. The units are correct. So this would earn a 1-1. Pretty cool. Pretty cool. In 4, the students convey the derivative of v with respect to t right here. They've conveyed that. But they've labeled this expression incorrect. That should be dv dt. They've labeled that incorrect. And remember, this is a really good example of notation and communication and how important they both are. Because this is labeled incorrectly, that student does not earn the second point. And finally, down here in example 5, this is a little bit of professional judgment, but the student has not conveyed enough to me of the derivative of v with respect to t. But they have labeled that final answer, or they've given me a final answer that's correct, with very minimal supporting work. So I think if I were grading this, I'd probably give that a 0-1. Pretty cool. Okay, in part B, the second point here was for, oh, in part B, pardon me, I take that back. Part B was worth 3 points. And so we expect that the student would start this problem by finding the second derivative, d squared h over dt squared. So in this process, the first point is for evidence of the correct use of the power rule. And here are 3 expressions. All 3 of these earn the first point. So those were the 3 most common expressions that students convey to us that earn the first point. And that's evidence of the power rule, evidence of taking the derivative of this expression with respect to h. The second point right here was for evidence of the chain rule. Now, most students, as you would expect, earn the first 2 points with just one line, with one expression. And so here on this line are some common responses that earned the first 2 points. And I won't read through all of those with you. I think you can look at those and see why each of those would earn the first 2 points. Specifically in this problem right here, the student does not earn the first point. Can you see why? There's a missing negative sign out in front here. But they do earn the second point. They provided sufficient evidence of the chain rule, so that earns a 0-1. Similarly, in this example, this was a common error also. The negative sign is there, but this 10 down here in the denominator, I believe, is incorrect. They provided sufficient evidence of the chain rule. This also earns a 0-1. So the third point in part B was for the answer with a sufficient explanation. Now, we've talked about this before. In many of the free response questions, there are eligibility criteria, and there was such here. So to be eligible for this third point, the student must have earned the second point. That's the chain rule point. And the second derivative of h with respect to t must appear. Now, the student has to say increasing, or it has to be consistent with their incorrect derivative. And again, that word explanation, at least the way that I interpret this, means that there must be some supporting work. So here are some examples. Here are 3 examples, I think, of supporting work. So if a student has an expression, the d squared h over dt squared of 1 over 200, or they leave something like that, I think I can tell that's positive. Or if they explicitly say that it's greater than 0. Student can certainly write that the second derivative is positive. They could write the derivative of dh dt is positive. All of those are sufficient explanation. So, okay, what I'm going to try to do here on this slide is put all of this together and show you how some of this might have been scored. Now, these are pretty minimal responses, but let's see here. This is pretty minimal for sure, but all 3 parts are here. Let's see. I see the power rule, I see the chain rule, and the student just says increasing. Okay, they don't see anything here about greater than 0, but I can look at that and see that. I can infer that. That student earns all 3 points. We can assume that the student sees that expression is positive. In this example, the student does not earn the power rule point. Can you see what's missing here? Let's see what's missing. It's the negative sign that's gone again. But they do earn the chain rule point. There it is. And this is a consistent answer with their derivative here, with their second derivative. So this is a classic example of a 0, 1, 1 in this problem. Let's see. In example 3, the student earns the first 2 points. This is correct, and they've got dH dt here. But you know what? There just isn't enough evidence to support the answer of increasing. I don't see anything in here about greater than 0. I don't see the explicit expression for dH dt, so this is a 1, 1, 0. In example 4, the student provided, let's see, some extra work that convinces us they know that this second derivative is greater than 0. Note the subtle difference between 3 and 4. I see that greater than or equal to 0. And yeah, pretty minimal. The student abbreviated increasing, but okay, we'll take it. We understand that one. And in example 5, the student does not earn the power rule point. Let's see why. Yep, okay, I see it. That's a 10 and not a 20. They do earn the chain rule point. They're eligible for the answer point, and let's see, the answer is consistent. Okay, so that's a 0, 1, 1. Pretty good. One of my favorite sort of parts of a problem to grade is the differential equation problem, and this part C was worth 4 points. A pretty typical distribution of points in this kind of a problem. First point here was for separation of variables. Here's some quick examples on how each one was scored. We'll interpret this line. Many students, by the way, are very familiar with this type of a problem. Many students start out right away by writing the integral sign. If we see something like that, we interpret this as separation of variables. That's worth 1 point. This is certainly separation of variables. All the h's are on one side, all the t's are on the other. Yeah, the dh can be out in front. That's okay. I always have a little trouble with example 3 here, but we do count this as separation of variables. In my class, this is not true, but on the AP calculus exam, it is graded as 1 point as separation of variables. I really want to see the differential separated. I want to see the dH on one side and the dt on the other, but we do accept this one. In example 4, there aren't any differentials in here, but in the presence of the integral signs, we're going to give this the point. In example 5, the student has not earned this first point yet. They could earn it with more work, but we don't have the integral symbols in there. The differentials aren't there, so that doesn't earn the first point. And in example 6, if this is all the work that we see on the page, this is a 0 out of 4. This is kind of a classic example of no separation of variables. That student doesn't earn any points in part C. Okay, the second point in part B was for the correct antiderivatives, and there was an eligibility criteria here. And this is kind of cool. I just want you to know that as we have graded these differential equation problems over the years, the grading of these problems has evolved and I think become even more efficient. And generally at each point as we grade this problem, there are eligibility criteria at each step. And here, there was an eligibility criteria. The separation of variables must be in this form with one of these values of k, one of these 6 values of k. So thinking about this eligibility, thinking about separation of variables, here are some examples on how each was scored. So here we have separation of variables. This is a valid separation. There aren't integral signs, but darn it, I believe that these are the valid antiderivatives, so this earns the first 2 points. Now note, there's no plus C here, but we're going to deal with that in the third point. I'm just looking at the first 2 for now. In example 2, let's see if I've got this right. There's a missing 10. But the separation is of an eligible form. I got to take a quick peek back up here and see that that k is equal to a -1. So yeah, that's okay. So they don't earn the first point for correct separation, but they are eligible for the correct antiderivatives, and I think they're both correct. So this earns a 0, 1. Now, example 3 is pretty minimal and unfortunately not communicated very well, but in the context of a high-pressure, high-stakes exam, this actually earns the first 2 points. I don't see the actual separation, but you know that many of your students are really good at this stuff. They can look at this kind of a problem, separate the variables in their mind, and start out by writing the antiderivative of both sides. So that's worth the first 2 points. The third point in part C was for the constant of integration and using the initial condition. So both of those things must be true, and there was an eligibility criteria here. At least one of the antiderivatives must be correct. The variable h cannot be part of a logarithmic function nor a linear function. We don't want the student to make this much more difficult nor even easier. And use of the constant of integration must be timely, and that means it has to be introduced at the correct point in the solution process. They can't get all the way down to the end of the problem and then all of a sudden say, oh, I've got to add this plus c in there. That just doesn't work. And the initial condition must be used, must appear before there's any bad algebra. So sorry about this, but here are 4 examples. This is the best way that I could come up with to sort of present this so that you could see all of these on a screen. I'm going to start up here in the top left-hand corner. In this example, there's an implied separation of variables. There are 2 correct antiderivatives right there. There is a constant of integration, an implied use of the initial condition, because there's the correct value of c. So this earns the first 3 points. I'm not sure about the communication. I'd really like to see a little bit more, but I see all 3 points for the scoring of this exam. I don't see the 4th one yet. I'm just looking at the first 3 for now in this problem, in this example. Over here on the right-hand side, top right-hand side, in this example, again, this implied separation, 2 correct antiderivatives, a timely constant of integration, right place, but there's bad algebra here using the initial condition. Can you see that? There's some bad algebra here. Let's see, what happened here from here to here? Oh, yeah, squaring both sides. We'll just square that, square that. We don't have to worry about squaring that binomial. So that's a 1, 1, 0, 0. Over here on the bottom left-hand side. In this example, the student earns the separation of variables point. I see it there. But they made an error in one of the antiderivatives. So where's the error? There it is right there. So they get 0 on the second point. They cannot earn the 4th point now. They're out of the answer point. But if they introduce a constant of integration and use the initial condition, they can earn the 3rd point, and this student has done that. And finally, over here on the bottom right-hand side, the student earns a separation of variables point, but their antiderivative on the left involves a logarithmic function. That's that kind of universal logarithmic anti-differentiation. And don't laugh, there are still many students who unfortunately write this. That student earns the 1st point for separation and nothing else. They're not eligible for anything else. Sorry, Vicki, I'm almost done here.
No, can you go back a slide?
Sure.
Okay, because we had a question about the one in the upper left-hand side.
Upper left,
about,
okay.
Or how the algebra, the C is actually changing, and the question is about subscripting it like C1, C2, and we do not require that on the AP exam, so I just thought you might want to address that just a second.
Sure. If that constant happens to change throughout, they don't have to subscript them. That's an excellent point. I'm just looking at this one kind of quickly here.
I think that's the one.
Square both sides. If they square both sides, I don't think anything's really changing here. That's the constant C.
Well, from the first line to the second line, where they divided by -20. So
Right. From here to here, it would indeed
yeah.
change. That's correct. And no, we don't require that the student subscript it. That's correct. Yep. It'd
Thank
be
you,
kind of
Steve.
neat if they did, but they don't have to.
Yeah, and some of my students kind of get lost in the subscript somewhere sometimes. So just through the years, I've realized it's actually better to just say, I don't know what the constant is, so if I divide it by -20, I still don't know what the constant is.
That's very good. I like that. Okay. In part C here, finally, that last point was for presenting a correct expression for H in terms of T. And the expression has to be our answer only. And here are some expressions that actually earn that point. I won't read through all of those with you, but I will remark down at the bottom here that this expression does not earn that final point. And the reason is because you have to solve, in this case, for H in terms of T explicitly. And
Well,
I
Steve,
will, yes.
that goes back to some algebra. For some reason, students read that solve for H in terms of T, meaning solve that it's got to be T equals. I don't know why that is
Really
bothersome to so many students in high school, but it makes me kind of wonder if maybe in some earlier classes, teachers possibly could spend a little more time on what that phrase actually means, because they'd struggle with it sometimes in the calculus class.
Interesting. I didn't think about that, Vickie. Okay, yeah, that's sort of the opposite of what we're asking for. Yeah.
Right.
Interesting, yeah. Interesting. Okay. All right, and finally, here are 4 more quick examples, and then I'll pass it over to you, Vickie. In this example up on the top left-hand side, we have implied separation of variables and integration, the antiderivatives. We have a timely use of the constant of integration and the initial condition. We have an explicit expression for H. Notice it doesn't say H equal, but that's okay. This earns all 4 points. Again, many of these examples that I'm showing you here are very minimal, but good examples to show you how the points are distributed. And let's see, over here in the top right-hand side, we have implied separation and integration, timely use of the C, but there's some bad algebra in here, isn't there, from this step to this step prior to the use of the initial condition. So this earns the first 2 points only. Bottom left-hand side, we have implied separation and integration, timely use of the constant C, I believe, and the initial condition. But again, there's some bad algebra in here, isn't there? Yeah, there's some crazy algebra in here. As we're solving for H, we squared on this side but took the square root on that side. So this would actually earn the first 3 points, but clearly not the last one. And finally, over here on the bottom right-hand side, we have some bad but eligible separation. One antiderivative is wrong, but we do have a correct or timely use of C in the initial condition. That's kind of a classic way to earn just that 1 point to 30. Wow. Thank you, Vickie, for putting up with all of that. I'm going to try to pass this over to you, okay?
Okay.
And here you are.
Okay. All right. So we're going to look at the TI-84, and we're unfortunately not going to spend a lot of time with the TI-84 because there's not a lot that we can do on the 84 without adding some programs. And I know that those of you who are 84 users may have some slope field programs and some things like that, but we just wanted to look at functionality that the TI-84 has that you might could use in your classroom. So I think students actually supporting work that they do after they've solved the differential equation to make sure that their solution is correct is a very valid use of technology. So I've taken the liberty to go ahead and graph the solution curve, which is the -1/20, and of course I have to put times x plus square root of 5, that quantity squared, in y1. We'll take a quick look at the graph, and I have also taken the liberty to change the window to something that would be realistic for the context here. So we see a nice decreasing function, which we should expect, and concave upward, which we should expect since we had found that rate in Part B was increasing. So let's look at how we could actually support this answer being the actual solution. So I'm going to go back to my y equals. And what I'm going to do now is in y2, I am going to say, well, let's look at the derivative of the supposed solution curve that I have in y1. And so I'm going to find my derivative, and that's going to be under my math, and it's number 8 in deriv. And so I want a derivative with respect to x, and I want to take the derivative of my solution, which is the expression in y1. So I need to find y1, which is under variables, and it's a y variable, and it's in function notation. And so there's my y1. And then I am going to do something that's a little bit unusual here, but I'm going to graph for all x. So I'm going to have x equals x. So let's just take a quick look at that graph. And so this is my derivative function that's showing up below the x-axis here. Okay, so that's nice. But how could I confirm that that is actually the derivative of the correct derivative? So I'm going to go down to y3, and now I am going to actually graph the HDT that I was given. So I am going to have negative 1/10, and it is going to be multiplied by the square root of h. But h is supposed to be the expression in my y1, so I'm going to go back and call upon my y1 and call it back into my equation here. So I went to variables, y variables, function, and y1. So essentially this is the derivative that we were given. So we're comparing the derivative we were given with the derivative that we actually found of the solution curve. So we should see the same graph. And so let's see if that happens. And I press enter, and I didn't need to press enter, but that helps. And then I press graph, and I see that black graph kind of is a repeat of the graph that was red, so that's y2 and y3, and that's sort of a visual confirmation that my solution curve is correct. So that's one way that the students could use the TI-84 without adding any programs or things like that. I want to also show you some things on the TI-Nspire that are very, very powerful. So I'm going to go to the TI-Nspire. We are going to be using the CAS version for this. And so let me just start a new document here. So File, New Document. And I want to add graphs. And I don't know how many of you have actually done this, but we're going to graph the slope field to visualize the solution curve. So when I add graphs, I can't graph this with our function grapher. So I'm going to go to Menu and go to Graph Entry Edit. And when I look here, I see that my bottom selection one is differential equations. And so that's where we'll be able to graph our slope fields. So I'll select number 8. And I need to input my differential equation, which is the negative 1/10 okay, 10, there we go, and it's the square root, so I'm going to multiply by the square root of my y, but since my prompt is y1 prime, I have to enter y as y1, and if you forget to do this, you won't see a graph. So I'm going to press enter, and I see that my slope field, actually this makes sense that I should only have positive y values. It actually makes even more sense to look at the first quadrant. So I'm going to go to Menu and my window zoom, which is number 4 here, and I'm going to do a first quadrant graph. So I've got just a little more visible information here. So I've got time from 0 to 20, and I've got heights from 0 to 13, which is really nice. And so I see a pattern here that I might be able to draw some solution curves, and students need to be able to draw solution curves on a given differential equation, one that we might produce for them on the AP exam. So in order to help the students actually visualize the specific solution curve, if I press Tab and go back to my Y1 prime, I can actually input my initial value. So I'm going to come down to the box here, and I think it was 0, 5 for that solving that differential equation. And when I press enter here, I actually see the solution curve. And if you think about it, that's the same solution curve we saw on the TI-84. I'll pop back over to it right quick. That's that same solution curve that we're visualizing there. Now, there's several neat things about this, but before I do any damage to this graph, I want to show you a way that the students can actually check their solution curve that they have, because this is just the differential equation with the initial condition. And this is a beautiful aspect of the TI-Nspire. So I can go to Menu, I can go back to my graph entry edit, and I can actually change it back to function mode. My slope field is still there. The solution curve that the slope field produced is still there, but now I can actually input my solution, which is negative, well, let me see, I need a parenthesis first, open parenthesis here. So we need negative 1 over 20 times, in this case we have to use x again because we're in our function grapher, plus the square root of 5. Let's see, I got to get out from under the square root sign, close my parenthesis, and then squared. And when I press enter, I should see that solution curve as a function overlaying the solution that the differential equation produced. Now, one of the neat things about the differential equation is that I can also come in here, and with the slope field, I can actually grab that initial condition and change my initial condition so that I can see other solution curves that are possible. And I think this really helps the students visualize possible solution curves that they might have to actually draw on the AP exam. So I'm going to pause just a second and see if anybody has any questions. Steve, is there anything we need to address?
I think this is a really cool example, Vicki, and one thing I just might mention, you might mention, is that when you have the calculator draw the solutions curve, not with entering f1 of x, but actually entering the differential equation, I believe, I'm not positive, but I believe that the calculator is drawing the solution curve in a way that students would do that with a piece of paper and a pencil.
Oh, I think so too.
I think in some sense it's following the line segments. Now, you know, it's using some numerical method in the background, but that's really cool because that's exactly what you do with a piece of paper and a pencil. That's really neat.
It absolutely is. We were going to show you the DE solve. Steve, we're kind of running short of time. You think I've got time to show them the DE solve?
Well, if you want to pass it back to me, I'll show them a quick screen.
Okay.
How about that?
That sounds good. All right, so share. Nope, assign. I always mess this up.
Okay.
It should be headed your way.
All right, fantastic. Okay, so I'm going to finish everything up with just one more thing here. This is actually part of the presentation that is TI in Focus AP Calculus. And so for every one of the free response questions, we have an extension video, which is a little bit more detailed solution of each of the free response questions and the use of technology, but also some extension problems. I'm just going to show you 3 of them here that are associated with this problem. So I won't read through everything here, but this is an example of an extension. This is just a little bit different DHDT, a similar situation with a similar cylindrical barrel, and we want to know when the height of the water is 4 feet, is the rate of change of the height of the water with respect to time increasing or decreasing? So it's a very similar question, but it's a different DHDT. Makes the student use some different techniques, some different concepts, makes them think a little bit more. I'm going to arrow down here if I can. I'm going to look at this one down at the bottom. Here's the technology solution that Vickie was discussing a moment ago on the TI-Nspire. I just think this is so cool. There is a function built into the Nspire called DE-solve, which will actually solve certain differential equations. And so without reading through this in gory detail, I'm able to enter the differential equation and the initial condition and let the calculator know what the independent and dependent variables are. And it comes back and gives me a solution. Now, Vickie and I were talking about this earlier. You'll notice that it has not solved explicitly for H there, and we're not sure why. We don't know exactly, I don't know exactly what the algorithm is going on in the background, but I'm still not stuck here because I used another function in the calculator called solve, and I just copied that expression down here and said, well, take that expression and solve it for H, and there's my answer. That's kind of cool. That's nice confirmation that, I got the right answer when I did it with a piece of pencil. Vickie was talking. Yes, go ahead.
Let me just mention something real quick. So the DE-solve on the older versions of the older operating systems of the calculator, the students had to sort of know the syntax order, which they could find under catalog. The new operating system is really nice because it brings up one of those template panels.
Yes.
And so it's much easier for them to decipher what they've got to actually type in order to solve the differential equation. And I encourage my students to check their solutions with this when they're not sure they've done it correctly. And if they see an error, then they know to go back to their actual solving of the differential equation, paper, pencil, and see if they can find the mistake.
This example down at the bottom of the page is exactly what Vickie just did with both TI-84 and the TI-Nspire. Well, with the Nspire, she was able to sketch the slope field. And although she didn't show you, there are, of course, programs for the TI-84 that will draw slope field. And here's one more. This is the problem that every student wanted to solve. This is a water tank that's the shape of an inverted cone with base radius 3. We have water being pumped into the tank at a certain rate, and we want to find the rate at which the water level is rising when the water is 4 meters deep. So that's pretty cool, too. Okay, Michael, I think we made it. All yours. I'm going to try to turn this back over to you.
Thanks so much, Steve. And Vickie.
There you are, sir.
I appreciate it. As we begin to wrap things up tonight, if there's any last-minute questions, please try to get those asked. I know Steve and Vickie will try to get those questions answered. We're super excited that the T-Cubed International Conference is coming to Dallas, just around the corner in a few short weeks here in mid-March. It's a great place to connect with people like Steve and Vickie and myself to learn a little more about technology or maybe expand your content or pedagogy. We'd love for you to visit our website, education.ti.com, to learn a little more about the upcoming international conference. As we mentioned at the beginning of the webinar, tonight we're giving away a T-Cubed International Conference registration, and tonight's lucky winner is Christine Gray. So, Christine, congratulations. We hope to see you as well as everyone else at the T-Cubed International Conference. Christine will be sending you an email here in a couple of days to give you a little more information. To receive your certificate of attendance, please go ahead and click the link that just appeared in the chat window. Also listed is a link for the documents that were used tonight. If you're watching this on demand, go ahead and copy that link into your favorite browser to receive your certificate. And if you're having any issues with these links at all tonight, have no fear. You'll automatically get a follow-up email in a couple days, and that follow-up email will contain links to the certificate, the documents, as well as the recording from tonight. Thanks so much, Vickie and Steve, for everything you shared tonight. I just wanted to add that if you've never attended an AP calculus reading, the scoring guideline that you see available online, if you never attended the reading, you might not ever know that that's gone into detail Steve and Vickie, you guys can correct me, but I think normally it's spent at least an hour, if not over an hour, with the readers, helping them understand the nuances, similar to what you did with us tonight, Steve, that it's not just a black and white, cut and dry kind of guideline, that it's maybe a little more fluid. So just
correct.
so people have a little bit of background as to why we took a little bit of time tonight to talk through each of those parts. Again, that was just one question. So Steve and Vickie, again, I appreciate everything you guys shared tonight. Thanks so much.
Thank you very much, Michael.
Thank you.
And thanks, everyone, for joining us. We hope to see you back online real soon. Have a great night.